In this lecture, we will discuss the manner in which costs behave. We will discuss fixed and variable costs. As part of this discussion, we will discuss learning curves. We will also discuss using past data to estimate a company's cost function. A cost function is a mathematical equation that gives you the amount of your manufacturing costs. As part of this discussion, we will talk about the high-low method of generating a cost function. In addition, we will discuss using a regression to generate such a function. Before we start our discussion, we will introduce the concept of a cost driver. A cost driver is also referred to as a cost base. A cost driver drives the cost in question. In other words, a cost driver causes a particular cost to change. For example, the more baseball bats you make, the more wood you need to buy. So, you can say that the number of units that we produce drives the material cost of our baseball bat manufacturing operation. For our discussion of cost behavior, we will assume that the number of units is the cost driver for our manufacturing cost. There are potentially many other cost drivers besides the number of units produced by a firm. For example, our manufacturing cost can be driven by the number of hours that our labor force work in a given period. First, let's talk about the cost function. We will assume that our total manufacturing costs are made up of two types of costs, fixed costs and variable costs. Fixed costs do not change. They are not affected by changes in cost drivers. In other words, regardless of the number of units that we produce, our fixed cost remains the same. The classic example of a fixed cost is rent. You pay the same rent whether you make 1 unit or 25 units. This graph shows the behavior of fixed costs. The x-axis is the cost driver, the number of units, and the y-axis is the total cost being measured. Regardless of the number of units being produced, our total fixed costs do not change. The graph that we saw is too simplistic. In reality, our manufacturing operation has capacity limits. At some point we will not be able to make any more units efficiently. At that point, we will need to expand our manufacturing operation. For example, we may need to rent another factory location. In reality, the rent cost looks like this new graph. It is a step function. The rent cost is fixed until you run out of capacity, then it jumps up to reflect the cost of renting an additional factory. So, why does everyone use the first graph with a single step? We use it because, normally, we are talking about a firm's costs over a smaller range of production. For example, we are discussing a firm's costs if they produce from 10,000 baseball bats to 20,000 baseball bats. This smaller range of production is referred to as the relevant range. The relevant range in this graph is indicated by the oval. Within the relevant range, the fixed costs are a straight line, and if we are only talking about the relevant range, then we can graph fixed costs as shown in this graph. Variable costs change as their associated cost drivers change. As you can see in this graph, the total costs are reflected on the y-axis, and the cost driver, which is the number of units, is shown on the x-axis. As the number of units goes up, the total cost of our baseball bat manufacturing operation also goes up. The linear representation of a variable cost function as a straight line with a constant slope is again an oversimplification of the behavior of variable costs. For example, the existence of economies of scale would cause total variable costs to increase at a decreasing rate, rather than a constant rate. This would result in a curved total cost function, rather than a straight line. When you consider the effects of economies of scale and learning curves, the variable cost function would curve as shown in this graph. However, we are not usually talking about the full range of possible manufacturing output. Rather, we are usually talking about a limited, restricted or relevant range of production. Again, we are showing the relevant range as the oval indicated on this graph. When only the relevant range is considered, the nonlinear cost, within the circle, appears more linear. The fact that we are usually discussing manufacturing costs within the relevant range, makes our assumption that we are dealing with a linear variable cost function more realistic. It also explains why variable costs are usually shown as a linear function. If you add together a firm's fixed costs and variable costs, you will have the firm's total costs. We now want to create an equation for total costs. We know that total costs are equal to a firm's variable costs plus its fixed costs. Variable costs are driven by the number of units produced, or some other cost driver. Total variable cost is made up of two components. The first component is the variable cost per unit, which can be represented with AV. The second component is the number of units produced, which is X. So, a firm's variable costs are its variable cost per unit times the number of units that it produces and sells. Fixed costs can be represented by a single variable, which is F. The units produced are not included because fixed costs do not change with the number of units produced. Using these variables, we can represent the linear cost function as total costs, which is TC, is equal to V times X plus F. The total cost function that we just derived is the red line represented in this graph. As you will recall from high school, the formula for a line is y equals m times x plus b, where m is the slope of the line, and b is the y-intercept. In this graph, y is the total cost. The slope of the line is the variable cost per unit, which is v, and the y-intercept is the total fixed costs, which is f. This graph shows that the total costs are made up of the firm's variable and fixed costs. The area under the red line represents the total cost of a firm. As you can see, the area from the x-axis up to the y-intercept is the fixed costs, and the area from the y-intercept up to the red line is the variable costs. We will now discuss using past data to estimate our cost function. We will discuss two methods to accomplish this. The first method is the high-low method, and the second method is the ordinary least squares regression. The second method is often called an OLS regression or just a regression. A simple way to estimate a linear cost function from your past costs is the high-low method. It is something that you can do quickly without the use of a computer. As you will recall, only one line runs through 2 points. Thus, you need only 2 points to define a linear cost formula. The high-low method says that the 2 points that define the cost formula are the highest activity level and the lowest activity level. Let's do an example. Assume that a company makes baseball bats, and that we have recorded the number of bats produced and the cost to produce those bats for each month last year. In its highest activity month, the company produced 40,000 baseball bats at a cost of $500,000. During its lowest activity month, 20,000 baseball bats were produced at a cost of $300,000. If you were to use the high-low method, you would first calculate the variable cost per unit, which is the slope of the linear cost function. We will first derive the variable cost per unit, which is the slope of our linear cost function. You can derive the variable cost per unit using the formula for the slope of a line that you learned in your high school geometry class. That formula is y1 minus y2, divided by x1 minus x2. y1 is the cost for the highest activity month, and y2 is the cost for the lowest activity month. Similarly, x1 is the activity level in the highest activity month, and x2 is the activity level in the lowest activity month. We now plug the cost and activity levels for the 2 months into the equation for the slope of a line, and we get $500,000 minus $300,000 divided by 40,000 units minus 20,000 units. This formula tells you that the variable cost per unit for our company is $10 per baseball bat. So far we know that our cost function is total cost equals $10 times the number of units plus the fixed costs. Now that you know the variable cost per unit, you can figure out the fixed cost. Take your linear cost formula and plug in the total cost and activity level for one of the 2 months that you use to determine the variable cost per unit. You then solve for the fixed cost. You can use either the high or the low point. It doesn't matter which month that you use. The data from either month will give you the same fixed cost. Using the data for the highest activity month, you get $500,000 equals $10 times 40,000 units plus the fixed costs. This becomes $500,000 equals $400,000 plus the fixed costs. When you move the $400,000 to the other side of the equation, you get $100,000 equals the fixed costs. If you use the lowest activity month, you will get the same amount of fixed costs. Using the data for the lowest activity month, you get $300,000 is equal to $10 times 20,000 units plus the fixed costs. Moving the $200,000 to the other side of the equation, you get $100,000 equals the fixed costs. Please remember that the activity level sets the high and low points. They are not determined by the dollar cost. For example, the month that produced the highest number of units is the high point, even though another month had higher costs. Ordinary least squares regression is also called OLS regression and regression. As was true with the high-low method, regression analysis also involves estimating linear cost relationships from past data. Rather than merely drawing a line between 2 points, however, we use the computer to calculate the line that best fits the data. With OLS regression, the computer squares the distances between a proposed cost function line and the actual cost data. In the graph that appears on your screen, the moving red line is the proposed cost function that the computer is considering, and the 4 dots represent the actual cost data. One side of the changing green squares is the distance between the actual cost and the estimated cost generated by the cost function. This distance is the difference between the estimated cost and the actual cost. This is the error in the estimate generated by the cost function. The green square is the error amount squared. The changing yellow box is the sum of all of the green boxes or the total squared errors. The computer finds the line that produces the lowest sum of the squared errors. The line in the center figure produces the lowest sum of these squared distances, and that is the cost function that the OLS regression would generate. With an OLS regression, you have an independent variable and a dependent variable. The dependent variable is the variable whose behavior you are trying to estimate. In our case, the dependent variable is the total cost. The independent variable is the variable that causes the dependent variable to change. In our case, the independent variable is the cost driver. You can have more than one independent variable. If you only have one independent variable, this is called a simple regression. If you have more than one independent variable, this is called a multiple regression. You now see the output from a regression that was generated by Excel. The regression estimates a company's cost function where we have provided the computer with the monthly cost and hours worked for 12 months. Using the hours worked as the cost driver, the regression has given you a cost function. The cost function appears under coefficients in the red box. The coefficient of the intercept is the estimated fixed cost. The coefficient of the x variable 1 is the variable cost per hour worked. The cost function estimated by this regression is total cost equals $3.81.393179 per hour plus fixed costs of $219,385.30.11. Next to the coefficients, in the green box, you will see the t-statistic for the fixed cost and the variable cost per hour. These t-statistics tell you how much confidence you can have in the accuracy of the cost function coefficients. The t-statistics in this regression are very high. In real life, if you saw a t-statistic of around 1.96, you would be very happy. In the blue box, next to R-square, you have how well the cost function that the regression estimated fits the actual cost data that you supplied. In this regression, the regression's estimated cost function explains 99.07% of the behavior of the actual data. Some people refer to the R-square as the model's goodness of fit. In this slide, we used the units produced as the cost driver. The cost function that was estimated by the regression is total cost equals $18.02797203 per unit plus fixed costs of $379,984.84.85. As you can see, the t-statistics of the coefficients of the regression's estimated cost function are once again very high. As was true before, the R-square of 0.984378363 is very high. The model explains 98.44% of the behavior of the actual data. In this final regression slide, we used both the hours worked and the units produced as the cost drivers. Because there are two cost drivers, this is referred to as a multiple regression. You can see that under coefficients, you now have a coefficient for x variable 1 and x variable 2. The regression has estimated that your cost function with two cost drivers is $3.86535522 per hour plus negative 24.461771 per unit plus fixed costs of $217,229.95.46. If you look at R-square, you see 0.99071704, which is almost the same R-square that we had when we used hours worked as the sole cost driver. So, adding units produced as a cost driver did not add much to our cost function. Moreover, if you look at the t-statistics, you will see that they are now significantly lower than the t-statistics we had with the simple regressions using one cost driver. What is going on here? The lower t-statistics with the same R-square is telling you that the model is still predicting the total costs very well, but the regression can't tell which of the two cost drivers is doing the explaining. This is due to the fact that our two cost drivers are correlated. You can only do a multiple regression when the two cost drivers are not correlated. So, you have to drop one of the cost drivers, and use a simple regression. When you first start to produce a product, your manufacturing cost per unit drops as you learn how to make the product. For example, if you were to buy 3 bookcases that you needed to assemble, then it is likely that the first bookcase would take longer to assemble because you read the directions very carefully and studied the parts involved. The second bookcase will probably take less time because you do not have to read the instructions all over again and you are familiar with the parts involved. Instead, you will probably briefly review the instructions. When you assemble the third bookcase, you probably do not even have to look at the instructions, and it takes you even less time to assemble. This phenomenon is referred to as a learning curve. Learning curves acknowledge that incremental manufacturing costs drop as the firm makes more units. Learning curves just happen. You cannot plan on having a specific learning curve. It is what it is. It is a phenomenon of nature that you are experiencing. All we are trying to do is to describe this phenomenon so that we can use it to estimate the manufacturing costs that we will have in the future. Learning curves are similar to economies of scale, but they are not the same thing. With a learning curve, your marginal costs decrease because you have more experience in making things. With economies of scale, your marginal costs decrease because you make more units. When you make more units, you get more experience, which is why these two phenomena are related, but they are not the same thing. When you make 20 violins a year for 20 years, your experience grows with each year, and this experience would cause your marginal costs to drop each year. For example, you learn over time that you only have to use 2 coats of varnish instead of 1 coat. This example involves learning curves, but not economies of scale. If you make 10,000 bookcases, your wood supplier will give you a cheaper price for materials than he would charge his regular customers because of the volume of materials that you are purchasing. This cost reduction involves economies of scale, but not learning curves. Understanding learning curves is important in startup situations. For example, in 1960, no company dominated the ballpoint pen industry. Bic, a French pen company, entered the United States ballpoint pen market by selling its now classic, Bic Crystal ballpoint pen. At the time, common, everyday ballpoint pens cost around 29 cents each. Bic understood the learning curve, and it knew that as it made more pens, the manufacturing cost of each pen would drop. Bic, therefore, offered the Bic Crystal ballpoint pen at a price of 10 cents, which was below its then manufacturing cost. Bic correctly assumed that the lower price would result in more sales. The increased sales would, in turn, result in cheaper production costs per unit. The end result would be that the price charged would be higher than the eventual unit production cost, and Bic would make a profit on its ballpoint pen sales. Bic's assumptions were correct, and it quickly dominated the ballpoint pen market. Today, 14 billion Bic Crystal ballpoint pens are sold throughout the world each day. Because Bic was able to anticipate the effects of the learning curve, it was able to dominate the world ballpoint pen industry. Learning curves can measure the reduction in cost to make a unit or the time it takes to make a unit. For the moment, we will call the thing being measured, the learning curve item. We will discuss the exact nature of the learning curve item in a moment. There is a common way to describe the learning curve that you are experiencing. Every time your production doubles, your learning curve item drops to a percentage of what it was before you doubled production. This percentage drop after doubling production is the common tool used to describe a learning curve. In this slide, you are looking at an 80% learning curve. The learning curve item was originally $12.50. When production doubled from 1 unit to 2 units, the learning curve item dropped to 80% of $12.50, which is $1,000. When production doubled from 2 to 4 units, then the learning curve item dropped to 80% of $1,000, which is $800. When production doubled from 4 to 8 units, then the learning curve item dropped to 80% of $800, which is $640. The 80% learning curve that we used in the previous slide was just an example. In this slide, you can see the percentage of learning curves that have been reported in the past for the industries listed. As you can see, they range from 75% to 95%. This slide shows the 80% learning curve that we discussed earlier. We can calculate the learning curve item for 1, 2, 4, or 8 units using the 80% rule that we discussed, but what about the learning curve item for 3 units? The formula given at the bottom of the slide can be used to figure out the learning curve item for every unit. In the formula specified at the top of the slide, Y represents the learning curve item that we are trying to calculate. A represents the learning curve item for 1 unit. X represents the number of units for which we are trying to determine the learning curve item. B is a formula, which is made up of the natural log of the learning curve percentage divided by the natural log of 2. Using this formula to determine the learning curve item for 3 units, we would first calculate b. b is made up of the natural log of 0.80, which is negative 0.22314 divided by the natural log of 2, which is 0.6931. When you divide these two numbers, you get b, which is negative 0.322. Putting b into our equation, we get 1250, which is the learning curve item for the first unit, times 3, which is the number of units for which we want to calculate the learning curve item, to the negative 0.322 power. This formula tells you that the learning curve item for 3 units is 877. What is the learning curve item that we have been describing in the prior slides? Generally speaking, it is either the cost to make a unit, or it could be the hours that it takes to make a unit. Assume for the moment that our learning curve measures the incremental cost to make a unit. This is referred to as an incremental cost curve. How would we calculate the total cost to make 4 units using an incremental cost curve? We would add together the cost to make the first, second, third and fourth unit in order to get the total cost. That is not very hard for 4 units, but what if you are talking about 1,000,000 units? No one wants to add up 1,000,000 unit cost figures. In order to avoid this, learning curves are often said to measure the average cost to make each unit if you make the number of units indicated. This is referred to as an average learning curve. With an average learning curve, in order to get the total cost to make 4 units, you would take the learning curve item for the 4th unit, which represents the average cost to make each unit if you make 4 units, and then multiply the average cost by the number of units involved, which is 4 in our example. The learning curve items are measured the same way using incremental or average learning curves. Only the interpretation of the learning curve item is different. In this slide, our learning curve is an 80% incremental learning curve that gives you the time it takes to make each unit. As you can see, the learning curve items are the same as we calculated before. The interpretation for this incremental learning curve is that it takes 1250 hours to make the first unit, 1000 hours to make the second unit, 800 hours to make the fourth unit and 620 hours to make the 8th unit. In this slide, our learning curve is an 80% average learning curve that gives you the average time it takes to make a unit at a given level of production. As you can see, the learning curve items are the same as we calculated before. The interpretation for this average learning curve is that it takes 1250 hours to make the first unit. If we make 2 units, then it takes us, on average, 1000 hours to make each of those 2 units. If we make 4 units, then it takes us, on average, 800 hours to make each of those 4 units. If we make 8 units, then it takes us, on average, 620 hours to make each of those 8 units. In this slide, you can see how the different interpretation given to the numbers reported by the learning curve will give you different total costs. With the incremental learning curve, the total hours to make the first unit is 1250. The total hours to make 2 units is the hours that it took to make the first unit, 1250, plus the hours that it took to make the second unit, 1000. So, the total is 2250 hours. The total hours to make 3 units is the hours that it took to make the first unit, 1250, plus the hours that it took to make the second unit, 1000, plus the hours that it took to make the third unit, 877.6. So, the total is 3128 hours. The total hours to make 4 units is the hours that it took to make the first unit, 1250, plus the hours that it took to make the second unit, 1000, plus the hours that it took to make the third unit, 877.6, plus the hours that it took to make the fourth unit, 800. So, the total is 3928 hours. On the other hand, with the average learning curve, the total hours to make the first unit is 1250. The total hours to make 2 units is the average hours that it takes to make each unit if you make 2 units, which is 1000 hours times the 2 units made. So, the total is 2000 hours. The total hours to make 3 units is the average hours that it takes to make each unit if you make 3 units, which is 877.6 hours times the 3 units made. So, the total is 2633 hours. The total hours to make 4 units is the average hours that it takes to make each unit if you make 4 units, which is 800 hours times the 4 units made. So, the total is 3200 hours. This slide shows you how you can calculate the time that it takes to make each unit when you are using the average learning curve. With the incremental learning curve, the learning curve item is the time it takes to make the unit in question, but with the average learning curve, the learning curve item is the time that it takes on average to make 1 unit if you make the number of units in question. What if you want to know the incremental time it takes to make a unit when you are using the average learning curve? That is what we are now going to discuss. If you look at the total number of hours that it takes to make a given number of units, and then subtract the total number of hours that it takes to make 1 fewer units, then the difference is the time it takes to make the last unit. You can see this with the incremental learning curve. It took 2250 hours to make 2 units and 1250 hours to make 1 unit. 2250 minus 1250 gives you the time it takes to make the second unit, which is 1000 hours. Similarly, it took 3128 hours to make 3 units and 2250 hours to make 2 units. 3128 minus 2250 gives you the time it takes to make the third unit, which is 878 hours. Moreover, it took 3928 hours to make 4 units and 3128 hours to make 3 units. 3928 minus 3128 gives you the time it takes to make the fourth unit, which is 800 hours. We obviously don't need to do this with the incremental learning curve, because the learning curve item is the time it takes to make the next unit, but it demonstrates how you can calculate the incremental time of the next unit by looking at the total times. Where this procedure comes in handy is when you are dealing with average learning curves. Here your learning curve item does not represent the incremental time to make the next unit. Instead, it represents the average time to make each unit if you make a given number of units. When you look at total times, however, you can calculate the time it takes to make the last unit. Using the average learning curve totals, it took 2000 hours to make 2 units and 1250 hours to make 1 unit. 2000 minus 1250 gives you the time it takes to make the second unit, which is 750 hours. Similarly, it took 2633 hours to make 3 units and 2000 hours to make 2 units. 2633 minus 2000 gives you the time it takes to make the third unit, which is 633 hours. Moreover, it took 3200 hours to make 4 units and 2633 hours to make 3 units. 3200 minus 2633 gives you the time it takes to make the fourth unit, which is 567 hours. This slide uses the incremental times that we calculated in the last slide and graphs them for both the incremental and average learning curves. The blue line is the 80% incremental learning curve and the magenta line is the 80% average learning curve. As you can see, the learning effect is initially greater with the average learning curve even though both lines represent 80% learning curves with the same learning curve items. This difference comes from the different interpretation given to each learning curve. The end.